Hello, everyone. Let us just very briefly sum up what we have learned in the last two classes. We have just learned that in case of a molecule, apart from electronic excitation levels, we also have vibrational energy levels and rotational energy levels. And we have seen how they originate and that there can be transitions between rotational levels, which gives rise to pure infrared rotational spectrum, which happens only in certain molecules that we have seen, which has a permanent dipole moment in the ground state. And there can also be transitions from rotational levels, as it is shown here. This is the upper vibrational level. This is the lower vibrational level. These are the various rotational levels in the upper vibrational level. These are the various rotational levels in the lower vibrational level, and transitions between the rotational levels of one vibrational level to another vibrational level gives rise to rotational vibrational transitions. And these are also governed by certain selection rules. And the selection rule for vibrational transition is delta V is plus minus 1. That is, it can change by 1 quantum. And for rotational transition, the rotational quantum number can change by 0 or plus minus 1. That means there can be no change in delta J, or there can be a plus 1 or minus 1. And for absorption, which is shown here in this slide, for absorption, delta J equal to 0 for Q branch. That is, as we have seen, it has a very small frequency width. Delta J is minus 1 for P branch, and delta J is equal to plus 1 for R branch. Now, going further, you see, when we discussed vibration of a molecule, we considered the most simplest molecule, that is a diatomic molecule, which has two atoms separated by the bond length. And these atoms vibrate in a simple periodic motion about their internuclear axis, right? Back and forth. And this was a very simple motion. But then we do not have only diatomic molecules. We have triatomic, tetraatomic, pentaatomic, and so many, right? So as we can imagine that the number of modes of vibration that are possible with increasing number of atoms will be much, much more diverse. More the number of atoms in a molecule, more will be the modes of vibration. So how do we know what are the number of modes of vibration that a molecule, say with n atoms, can have? So let us just consider a molecule with n number of atoms. So we know that the number of degrees of freedom for n atoms is 3n. Total number of degrees of freedom is 3n. Out of these 3n, what are the number of degrees of freedom that are required to describe its translation motion in the x, y, z coordinates? So that is 3. So the 3 degrees of freedom are required to describe its translation motion. And you also require 3 degrees of motion to describe its rotational motion about the 3 orthogonal axes, x, y, z axis. The rotation of the molecule can be described in 3 degrees of freedom. So the remaining, that is 3n minus 6. 3n minus 3, which is the degrees of freedom required to describe translation motion, minus 3 required to describe the rotational motion. So 3n minus 6 will be the total number of the vibrational degrees of freedom that are possible for a given molecule with n number of atoms. So this is a very easy formula for us to know what are the number of normal modes of vibration. These are also called normal modes of vibration or fundamental modes of vibration, because basically these are independent of each other, and any complex vibration that a molecule may exhibit, it can be broken down or it can be expressed as a linear combination of these normal modes of vibration or fundamental modes of vibration. Now, in case of a linear molecule, you see, this kind of a motion is not allowed about this axis, because here the molecule remains unchanged as it rotates about this. It is unchanged, and therefore this motion is not. It is not a. It cannot be considered rotationary motion, and therefore for a linear molecule the number of degrees of vibrational freedom motion are 3n minus 5. So when we say diatomic molecule, it is always linear. We were considering nitrogen molecule. Nitrogen is homonuclear diatomic molecule. So the number of with n is 2 in case of a diatomic molecule. So then 3n minus 5, because it is a linear molecule. So it is 6 minus 5, that is 1. So it has only one mode of vibration, which we had seen earlier, that it moves in, goes out about without the center of mass moving or shifting. So this is the only one possible mode of vibration that is possible in case of any homonuclear diatomic molecule, and therefore a diatomic molecule will have a ladder of vibrational levels, and this ladder, it will have only one particular such ladder because there is only one vibrational mode possible. Now in case of if you consider now if we consider a triatomic molecule, for example H2O molecule, now your number is 3. So, and it is not a linear molecule. A hydrogen molecule is something like, a water molecule is something like this. And there is an angle of say 107, I think, about 107 degrees. So this is not a linear molecule. And so what you have is 3n minus 6. So that gives rise to how many? 3n, 9 minus 6, that is 3 number of normal modes of vibration. Same thing if you consider a CO2 molecule, which is the linear triatomic molecule. So it is a linear triatomic molecule, and therefore for this, you have, although n is 3, the number of degrees of vibrational freedom are 3n minus 5, and therefore the number of vibrational modes, fundamental modes of vibration are 4. Similarly, you can think of ammonia. Ammonia is NH3. It has 4 number of atoms. It has a trigonal pyramidal shape. It is not a linear atom, linear molecule, therefore, and it has 6 degrees of freedom. And so in this way, each molecule, you can deduce the number of vibrational degrees of freedom it possesses. So as we saw in case of CO2 molecule, it has 4 vibrational modes, normal modes of vibration. And as I told before, any complex mode, a complex vibration of the molecule can be described or can be broken down into a linear combination of these modes. And therefore, these are called the fundamental modes of vibration. Now, coming to a carbon dioxide molecule, we just saw it is a linear, symmetric triatomic molecule. And so the number of modes are 4. What are these modes? Let us try to understand, because these vibrational modes of a CO2 molecule play a very important role in the lasing process in a CO2 laser. So the first is symmetric stretch mode, where you have the central C atom, which remains stationary, and the oxygen, which is on the either sides, it moves inward. So that means the bond gets compressed, then it recovers, comes back to its original position, then stretches outward. So that this bond expands. So basically, in the first half cycle, it gets compressed, comes back to its position. Then in the next half cycle, it expands and again comes back to its mean position. So while the center atom remains stationary, the outward oxygen atoms symmetrically stretch outward and inward in a periodic fashion. And therefore, this is called a symmetric stretch mode. And the energy that is required to excite one quantum of this vibration is 1388 centimeter inverse. Now, or which can be converted into energy and it gives this. Now, I do not know whether you are aware of what is centimeter inverse, but spectroscopists use this as a very convenient unit to actually talk about energies in these vibrational, rotational, or even electronic states. So how do you get this? You see, E is h nu. So you can write it as hc by lambda. So E by hc is equal to 1 by lambda. When lambda is taken in centimeter, so this has a unit of centimeter inverse. So therefore, this centimeter inverse, you can see, is directly related to energy. So larger is centimeter inverse, larger is the number that you get here in centimeter inverse, implies that much higher is the energy. One useful thing to remember at this point is room temperature, that is maybe 30 degrees Celsius, or if we take, then the energy that these gas molecules possess is given by kT. This is 200 centimeter inverse, and this can also be given in terms of electron volt as 0.025. This will, as we remember this will give us, it will enable us to compare between various energies and how it compares with the thermal energy of the molecules, etc. And it will be useful for us to get a kind of semblance of what energy levels or what energy values we are talking about. So the first one we saw is the symmetric stretch. The next one is bending mode. See, once again, you have your carbon atom at the center and the two oxygen atoms to the side. But because of the vibration, the carbon atom moves upward and the oxygen atoms move slightly downward so as to maintain. See, in the vibration, your center of mass doesn't change. And therefore, to maintain the center of mass at the same point, the oxygen atoms move slightly downward in the first half. Then they come back to the mean position, and then this carbon atom moves down, and then the oxygen atoms move slightly upward. So this bending motion, in this bending motion, what you have is, you can see that the linearity of the molecule is changing, right? Your carbon atom is moving up and down, and these oxygen atoms also go in tandem in the reverse direction so as to maintain the center of mass at the same location. So this is one way where I'm saying that we are talking in the plane of this board, and the carbon atom is moving up and down while oxygen atoms are also moving in the opposite direction. The other possibility is that the carbon atom is moving perpendicular to the plane of this board, that it is going in and out, and so are the oxygen atoms. So these two modes, these are called degenerate modes because they have the same energy, and therefore for all practical purposes, these two bending modes are considered as a single, because they have same energy, we do not distinguish between them. We say that this is the bending mode. So, but then actually they comprise of two bending modes here. One is in the vertical direction in the plane of this board, and the other is perpendicular to the plane. As you can easily imagine, the quantum of vibration energy that is required for this is much less than that of symmetric stretch. It is very easy to actually break the linearity of the molecule, and this requires much smaller energy compared to symmetric stretch. And the third one that we have is asymmetric stretch. That means, as you can see here in this figure, the central carbon atom moves towards one of the oxygen, and this oxygen too moves towards this carbon atom. So this bond gets compressed or squeezed while the other one gets stretched because this oxygen atom moves outward. This movement is such that your center of mass remains as it was. Right? This is in the first half. And in the second half, the reverse happens. this oxygen atom moves outward, and this carbon atom now moves towards this oxygen, and this oxygen also comes in. So in the first half, this bond is compressed, this is stretched. In the second half, this is stretched while this bond is compressed. So this is the periodic compression and stretching which is happening, but the compression and stretching is not symmetric on both sides. You can see the asymmetry here, right? So this, when this is compressed, this is stretched, and when this is stretched, this is compressed. So this compression and stretching, this is the periodic motion, but because it is asymmetric, this is called asymmetric stretch mode. And the energy required for this, though I have not given you the value, but energy required for this is much, much more, as you can even generally understand from logic itself, that this energy required for this is much higher as compared to both bending as well as symmetric stretch. So I have just shown all the three in one. The first one is symmetric stretch, where the two bonds, they symmetrically get squeezed and stretched. Okay. And I have tried to show it with a small animation. I hope you'll be able to see it. Yeah. As you can see, this bond is, sorry. This bond is getting compressed and stretched. That is symmetric stretch. The second one is the bending mode, where you have the central one going up and down, right? Central one going up and down, while the other oxygen atoms also move in tandem to keep the center of mass at the same position. And the third one is asymmetric stretch mode, where there is an asymmetry in the stretching. Yeah. So you can see that there is an asymmetry in stretching. While one gets stretched, the other one gets compressed. And so we also have learned that this is degenerate. Basically, it can have the carbon can go in this plane, or it can go perpendicular to the board, and therefore these two modes are degenerate. So a CO2 molecule, when it is in the ground vibrational state, we can show its position in terms of V1, V2, V3, where V1, V2, and V3 are the vibrational quanta corresponding to, this is symmetric stretch mode, this is the bending mode, and this is the asymmetric stretch mode. So any vibrational state of a CO2 molecule can be told in terms of these three vibrational quantum number, and this is represented as, suppose it is in the ground state. So in the ground state, all these three are 0. This is the ground vibrational state. Now suppose the CO2 molecule has one symmetric stretch. So in that case, it can be written as, when it is one symmetric stretch, that means V1 and 0, 0, because the other two are not there. So it is 1, 0, 0. So it has one quantum of energy for the symmetric stretch. So any complex vibration, suppose we say V1, V2, V3 equal to 8, 2, 3. What do we understand from here? We understand that this particular molecule is having 8 quanta of vibrations, 8 quanta of symmetric stretch mode vibration, 2 quanta of bending mode vibrations, and 3 quanta of asymmetric stretch mode. So this is the kind of nomenclature one normally makes use of. And in future, we will talk of the vibrational levels of CO2 molecule using these three quantum numbers, V1, V2, V3, and their corresponding quanta of vibrations. So now, having understood the various vibrational levels of a CO2 molecule, we now come to the operation of a CO2 laser. Okay. Now, as we have seen, it has four modes of vibration, of which two are degenerate. So, in all, we consider three levels, three vibrational modes. All these three play their part in making a CO2 laser. How we understand? So, you have this is the CO2 ground level where we are seeing it is 0, 0, 0, and this 0, 0, 1, that is one quantum of asymmetric stretch. Okay, so this acts as the upper laser level. You have 1, 0, 0, which is one quantum of symmetric stretch mode. This is the ground laser level. We have, sorry, this is the lower laser level. We have one more lower laser level, that is 0, 2, 0. I will explain why we have this. And then 0, 1, 0 and the 0, 0. So let me just explain how this lasing action takes place in very brief. And then we will come back to the details of it. We know that in case of a CO2 laser, we have the excitation takes place in an electric discharge. So the molecules in the ground level are excited in a discharge to the upper laser level, which we have shown as this 001 level. Once they come to the 00 level, and when an inversion is created between 001 and 100, okay, when there is an, because this, we at this point, let us assume that it is not populated. So when an inversion is created, then then stimulated emission sets in. The molecules from the upper laser level will come down to the lower laser level through stimulated emission. And then the molecules which are in 100, this 100 level and 020 level are very, very close. What is 020 level? It is two quanta of bending mode, right? One quanta of bending mode is 667. Two quanta is about 1285. Why there is a difference between these two? You should be able to explain now. You should be able to know why this is not exactly double of this. That I leave it to you so that you think and answer. Okay. So this 020 is very close to 100. 100 is one quantum of symmetric stretch. 020 is two quanta of bending mode. These two levels are very close, so close that the separation between them, as you can see, this is 1387 and this is 1285. It is less than 200 centimeter inverse. That means it is much less than the thermal energy that is possessed by these molecules. And therefore, through collisions, they are in a constant kind of exchange of energy, exchange of population, etc. So we can say that they are in some sort of equilibrium, right? So these two are 100 and 020 are in some sort of equilibrium. We call it Fermi equilibrium or Fermi resonance, but you need not go into that kind of a detail. We suffice it to say that these are very close and there is a constant exchange of population between these two through collisions. So the molecules from here come down to the lower laser through stimulated emission, by stimulated emission. And from here, the molecules can directly come here through collisions. So how it is? So let me just write down here. CO2 000 plus electron in the discharge with high energy will give rise to CO2 001 plus electron of reduced energy. So this is how population inversion is taking place. Now, from the population, now as the electrons go to the 001 level, so through stimulated emission, let us just consider one part of it. It comes down to 100 through stimulated emission. Now from 100, they can again collide with ground state molecules which are in abundance and come down to 010. Why? Because the energy difference between these two is much small, as we saw, and these are resonant collisions because the energy difference between twice of this, energy difference between this and this is nearly equal, and these are very close by. So by colliding with a molecule in the ground level, it can be risen to the 010 level, and this can come down to the 010 level. And so in this, what you see is when CO2 100 collides with a ground level molecule, it results in two molecules in the 010 level. Now, from 010 level, the molecule has to make a transition to the 00 level, to the ground level. And this is the bottleneck in the sense that this transition is not very fast, and it is only through VT relaxation. This is through collisions. This is called vibrational relaxation, because this is a vibrational excitation, this is a vibrational relaxation. Both are of nearly equal energy, and therefore it is very fast. It doesn't involve much of energy from neighborhood, and therefore these are very fast and they are efficient as well. But from here to here, when it has to come down, then it has to be through collisions. But you see, what is the energy involved? Energy involved is 667 centimeter inverse, while the average temperature is 200 centimeter inverse. That is what we saw of the gas molecules. So the change in energy here, quantum of energy that has to be exchanged with other molecules for coming down is very, very large. And therefore, this VT relaxation, what is this VT relaxation? It has to be converted into kinetic energy of the other molecule, which is bringing down this 010 molecule. So that VT relaxation is poor, and therefore this becomes the bottleneck of the lasing process. In the sense, molecules start getting accumulated here, and getting accumulated here means more the number of molecules here, smaller will be now this relaxation, right? Smaller the relaxation, then more will be the population here, and if population becomes more here, then it will kill the population inversion, and therefore the gain will be killed. So there is an immediate requirement for actually depopulating this lower reservoir. So we have very briefly today understood what are the fundamental modes of vibration, what are the 4 vibrational modes of a CO2 laser, and how they can be considered as 3. So we have 3, we are considering 3 normal modes of vibration, that is the symmetric stretch mode, bending mode, and the asymmetric stretch mode, and how the 4-level laser system of a CO2 makes use of all these 3 modes of vibration, 3 normal modes of vibration.